Hello everyone, welcome to this tutorial on TRMs. The Tiny Recursive Models came out a few months ago. It was an amazing paper and I thought it would be interesting for people to be able to play with it. For this tutorial, we are using our own implementation of TRM called NanoTRM. It reproduces the results from the paper, but also lets you play with TRMs more easily and also play with smaller data sets. So if you look at the original paper, the paper really is a gem, and it explains very well how the TRM works. However, it can be a little bit complex to understand its implementation. This is a high-level diagram of the architecture, and I will assume that you've read the paper. In particular, in the paper, there is the pseudocode for TRM, and it's very neat because it gives a good intuition of how the TRM works. You can see here the latent recursion loop, the deep recursion loop, and the higher level deep supervision loop. So when you look at this, you would expect in the code, for example, this for loop to appear somewhere, and it actually doesn't. There's a bit of a tricky way in how it's implemented. And the goal of this tutorial is to go deep into the code and explain how TRM is implemented. Okay, so let's get started. This is the main file in the code. It shows the main TRM architecture. And what we're going to do today, in hopefully just a few minutes, is run through this code. And at the end of it, you should have a much better understanding of how it works. Before I jump into the code, there are two things that we need to discuss on TRM that are really critical to understand the implementation. The first one is that the TRM architecture stores and maintains a latent representation of the problem Z and the solution Y, and those are stored in these structures here. So there is an inner carry called TRM inner carry and a higher level carry called TRM carry. The inner one maintains ZH and ZL, which represent respectively Y, the solution, and Z, the problem. And these vectors are maintained over time throughout the entire training. The second bit of the implementation that is interesting is the way the data is managed, because in the TRM, unlike a classical training where a batch is fed to training and then thrown away, in the case of TRM, a sample may be used multiple times during training because we want to let TRM iterate on it. So instead of implementing this as a for loop, what the implementation does instead is maintain whether a sample in the batch is finished or not. This is the halted flag here. And the code maintains the sample into the batch until it is done with it. And so what it means is that a given batch is actually dynamically maintained, and every time a sample is finished, it is replaced by a new one. So this is a little bit exotic, but it actually makes for a much easier implementation and much more efficient training. Okay. Now that we're done with this introduction, let's dive into the code. So this is the main architecture. By the way, we're using Lightning for easier experimentation. And we see here all the parameters of the TRM. We won't go through all of them, but you should be able to map them to the paper as we go. So when we create this module, the first thing we do is we set optimization automatic to false. The reason is that because the implementation is quite special and tricky, we can't rely on the automatic optimization of Lightning. We have to manually optimize ourselves. This is the input embedding. It essentially maps the input tokens into their representations. So in the case of ArcAGI, for example, each input is a 2D grid, and each cell in the grid is an integer. What input embedding does is transform this integer into a vector of hidden size. The second bit is the positional embedding, we can use 2D positional embeddings or 1D embeddings, or we can use no embedding at all. The third bit is the core of the reasoning module of the TRM. We have here its configuration, and the reasoning module itself, which we call le net, here is essentially a number of layers repeating this reasoning block. And then finally, we have two heads, one called LM head and the second called Q head. The LM head learns to predict the output that is expected from the model. The Q head learns to stop. In the original HRM paper, the Q head was learning to stop and to continue. In the case of TRM, it is simplified to just learning to stop. And so we have a single value here. Otherwise, it would be a 2. And then we initialize the latent representations in the carry structure. Last but not least, we have the puzzle embeddings. Puzzle embeddings are, as the name indicates, embeddings that represent the puzzles. They are also optimized for over time. And because these embeddings are very sparse, we use an in-house sparse embedding implementation of it. We'll get into it if we have time. Okay, the setup itself is fairly simple. I will skim through it. The essential idea here is that we compute the number of total steps. That's about it. The input embedding itself is also fairly explicit. It takes as input the input and then transforms it into the embedding that will be fed into the main reasoning logic. Then we have, I guess we should say on the puzzle embedding, the key in the input embedding is that we use both the input embedding and the puzzle embedding. And then we cut them together. Then we have a few utilities: initial carry, empty carry, reset carry. I won't go through them. They are fairly self-explanatory. They are essentially used to manage the carry structure. Now we're getting into the interesting bit. This part here is the inner forward loop. So this is the place where the data that comes from the batch is first transformed into its embedding and goes through the various iterations that you can see in the pseudocode of the paper. So as you remember, one of the key ideas of TRM is to actually not propagate the gradient during the first set of iterations. So the first h cycles -1 are done without grad. So here we update first the problem space multiple times, and then we update the solution vector. So this would be y. And then we do one last pass on z and y, but this time with grad. And then finally, last but not least, here we compute the output from the model, so the LM head and the Q head. Notice that the LM head here is then split to skip the first part of the output because we don't care about the transformation of the puzzle embeddings by the network. All we care about is actually the prediction from the model on the input. Okay, the forward function itself essentially resets the carry structure where needed. So when for the samples for which the data, the training was halted, it adds new data into it, and it calls the inner forward function. And then here, what it does is this place here is about halting. So essentially, this is where we decide to halt for a sample, no matter what, if we've reached the maximum number of supervision steps. But we also have some exploration mechanism here to help the head that's learning to stop do a bit of exploration to learn to stop at the exact right time. So not too early or not too late. So this part here implements implicitly the for loop that I showed before in the paper, where in theory we should be iterating a number of supervision steps, but this is actually implemented through this mechanism. Next, we have the compute loss and matrix function. This function is used during training to compute, as the name indicates, the loss and the matrix. So what we do here is we call the forward function on the carry and the batch. We get some outputs, and we also get the expected labels from the training data. Now, there's a bit of a trick here. This ignore label ID here is here because in the case of some problems like RKGI, the size of the input and the output could vary across training. For example, in the case of RKGI, some puzzles output tables of size 6 by 6 or 10 by 10, all the way up to 30 by 30. So the way this is handled in this code base is by using the maximum grid size, 30 by 30, and filling the blanks with a mask value which we call ignore label ID, and this is used to mask the computation of the loss. So we're doing this. These are metrics which are computed outside of the gradient descent. We compute the accuracy and the exact accuracy, and this is going to be used both for training and for validation. Then here, we compute the stable cross entropy. So we use a specific implementation called stable max cross entropy, but you should really think of it as the cross entropy between the logits of the output and the labels. And here, we compute the binary cross entropy between the expected Q-halt logits, so essentially the logits of the learning to stop function, and whether it was the right moment to stop. So essentially, what this loss is doing here is trying to maximize the likelihood that the training is going to stop at the right time and learn to stop when it has found the right solution. And then here we compute the final loss, which is the sum of the LM loss and the Q-halt loss. It is weighted by 0.5, but this is very much arbitrary and could be changed. Okay, and finally we get to the training step. So the training step here uses all the functions that we described so far. So it takes the batch as input, it fetches the optimizers, it initializes the carry structure if needed, and then it computes the loss and the matrix using the function we just went through. Given this loss, it then calls backward. We have a bit of gradient monitoring here, and then finally gradient clipping. Then we set the learning rate for the optimizers. There is a bit of a trick here because we essentially use, what this code does is that it uses a constant learning rate after warm-up. This is not always the case. Typically, we would use the learning rate schedule across the whole training, but in the case of TRM, this makes training more stable. And then here, this is the place where we actually step through the optimizer. Finally, we log the matrix we're interested in, and we update the manual step because, again, we disabled automatic optimization. The validation step follows the same logic. So we take the input data, we initialize the carry if needed, and we iterate through the samples. We use the same compute loss and matrix, and we do this through a while true function that implements a for loop throughout the supervision, and we know we are going to leave this function at some point, because at some point all the samples will have halted. In the worst case, if we've had to use the maximum number of supervisions for all the samples. And then we compute the metrics and log them. I think that's pretty much it. Then we're almost done. There's a lot of monitoring the gradient here. We're not that interested. Here we're logging the metrics. These are a bunch of utilities. And then the last interesting bit is the configuration of the optimizers. So the TRM actually maintains two optimizers. One is for the parameters of the main model, or the reasoning module. And the second optimizer is the specific sparse embedding optimizer for the puzzle embeddings. So we end up with two optimizers, which is why we find these optimizers in the training step. So that's pretty much it. There's a bunch of other tips and tricks in the optimization of TRM, but I thought it was useful to give this first high-level overview of the code. And then you can use this code to run experiments. So if you run a training following the instructions in the README, here is an example of a training happening on the maze dataset. So we can see here, we're right in the middle of the training, we're running through the epochs. The learning rate is actually constant over time, like I mentioned. We can see the exact accuracy and the accuracy increasing through training. And this bit here is interesting. This is the number of reasoning steps that decreases over time. At the maximum, it is 16, but we can see here that the model learns to stop early when it has found the right solution to a problem. It is quite interesting to see that in this example, it goes down from 16 all the way down to 6 steps are enough to find a solution to the problem. And then we have the corresponding metrics for the validation. We see the validation loss going down and the exact accuracy and the accuracy of the model going up nicely. Okay, that's it for today. I hope you found this tutorial useful. Feel free to check out the code and see you soon. Bye!